It's my great pleasure to welcome you all on behalf of my co-organizer Debopam Bhattacharjee and myself. My name is Ankit Singla. I'm a professor of computer networking and I run the network design lab in the computer science department at ETH Zurich. LeoCon has a very diverse audience, and I think I need to provide enough context to keep everyone on board. So my talk will address these three questions. What's this all about? Who cares? Who's involved? And what are the open challenges and opportunities in this area? So what is this all about? We'll discuss two big use cases for low Earth orbit networking. On the left here, using large constellations of satellites to provide internet service. And on the right, using smaller satellite fleets for imaging applications. We'll start with imaging because Day One's program primarily centers on this. Satellite imagery has numerous applications like monitoring natural phenomena such as volcanoes, forest fires, floods, keeping an eye on agriculture, land use, vegetation changes like in rainforests, understanding glaciers, evolution of ice sheets, and other phenomena that help us understand the planet's health, and many more such applications. Across all these applications, at a very high level, this is what's happening. A satellite or a set of satellites is taking pictures. Pictures is overloaded here. It can be any type of sensing instrument on a satellite that's producing sensor data. This data is then transmitted to ground stations, like this one here, over radio links, which then transmit the data to a cluster or data center facility where it can be processed, used in applications, stored, archived, etc. This here is a coarse summary snapshot of today's LEO imaging ecosystem. You have hundreds of satellites in orbit doing various imaging tasks. These satellites together produce tens to hundreds of terabytes per day of data. This huge data volume creates bottlenecks for both data download, getting that data down to Earth from the satellites, and data compute, processing of that data to produce actionable insights or information. These bottlenecks are at the heart of the networks and systems challenges that we are interested in. And these challenges are getting more and more urgent over time. I'll explain this urgency with a schematic here. On the x-axis here is the frequency with which we image a particular part of the planet. And on the y-axis is at what resolution we are doing this. How small are the smallest objects that we can distinguish in the imaging that we do. For a fixed cost system, there's a Pareto frontier, a trade-off between these two factors, and you can't do better than that, right? So either you can have high resolution imaging and do it infrequently, or do much more frequent imaging, but at much lower resolution. And there's various trade-off points along the curve. Now, the key thing is that this curve is shifting upward and rightward over time as the cost of satellite launches improves, decreases, the technology for imaging improves, the satellites get more miniaturized, etc. So there's a reduction in cost, and at the same time, there's increasing value and willingness to invest more money into this ecosystem of imaging as the market expands with more and more applications, partly enabled by convenient cloud processing. So these systems, satellite fleets, are evolving towards greater and greater scale. And as you can imagine on this right corner, as you keep moving towards rightwards and upwards with high resolution images taken more and more frequently, we get a huge data deluge and subsequently a processing or compute demand that's increasing very rapidly. And this is what's sharpening these systems and networking challenges involved. I'll discuss some of these challenges later, but let's first look briefly at what's happening on the broadband side as well. Here, the goal is to use hundreds or thousands of LEO satellites to provide internet connectivity. Such global coverage is meant to address the gaps in connectivity serving underserved populations, but also other challenging connectivity scenarios like on the seas and in flight. So how does this work? Each LEO satellite provides service in a coverage zone underneath itself, as shown here. Terminals in this zone can communicate with the satellite using radio frequency beams. A particular ground terminal can be seen from a particular satellite only for a few minutes, and thus requires frequent handoffs to successive satellites as they move around to maintain continuous coverage. A terminal S can send data to a destination T in several ways, one of which is to send it up to a satellite through a radio link, And then if the satellite constellation supports inter-satellite connectivity using lasers, for example, then you'll perhaps take several satellite to satellite hops and then downlink the data again to the destination using a radio link. Another way of doing this, if the satellite constellation does not have inter-satellite links, is to bounce the data back and forth between the terrestrial sphere and the satellites, as shown here. This is called bent pipe connectivity. Of course, there are many flavors of this. Another iteration would involve just getting the data from a source sender to a ground station, and then networking the ground station to the internet through terrestrial fiber, and using that terrestrial fiber connectivity to reach the destination. So these are several ways in which LEO connectivity can be implemented. Before the ongoing LEO networking revolution, prior satellite-based consumer broadband operated primarily in geostationary orbit, as shown here. With a handful of geostationary satellites, one can cover a large part of the planet, as this graphic shows, with this coverage cone. But this results in extremely large latencies or round-trip times, RTTs, because of the long distances involved. Geostationary satellites necessarily have to orbit at this altitude of about 36,000 kilometers. Operating in low Earth orbit allows much shorter RTTs, and latencies can be comparable to terrestrial fiber networks. In fact, across long distance communication, these networks, LEO networks, can be faster than fiber routes. One flip side, however, is that the coverage cone of a satellite is now much smaller just because of the visibility a satellite has. And we need many more to cover the globe. We'll use a schematic again to look at the design space here. On the x-axis is some notion of coverage, network capacity, market size. It's deliberately loose. And on the y-axis is latency that the network provides. There are at least two incumbent providers that use a handful of GEO satellites to serve about 1 million customers, providing latencies of about a few hundred milliseconds. There's also at least one incumbent provider in the LEO networking space with tens of satellites, which in theory could provide a few tens of milliseconds of end-to-end latencies, but it serves primarily niches like satellite telephony. The new constellations are on track to occupy this spot on this plot. That is massive scale in low Earth orbit. Such networks can serve tens of millions of customers. SpaceX has already filed requests for serving about 5 million customers in the US. And they've already demonstrated measurements with 20 to 30 milliseconds of latency round trip. And this is with partial deployments of their constellation. So this is roughly the space where the new massive scale LEO constellations are on target to operate. We could move further rightwards here. This will largely depend on how much market demand there is for such connectivity. This is not clear yet. Regardless, these networks, even at this minimal scale that I think we'll hit very soon, are high value, complex, and dynamic. Many of the network and system challenges that we saw in the LEO imaging space are even exacerbated here because of the scale of these networks. So this bottom line connects these two themes today, and that's why we are addressing them both together at LEOCon. So now let's move on to the second question. Who cares? Who is involved in this space? So I hope that I've given you a sense of the interesting applications involved and why they are of value. But I also want to touch on recent industry developments. There's quite a lot of hectic activity in both spaces. On the imaging side, Azure and AWS recently launched ground station as a service platforms of their own. Google and Planet Labs are partnering on imaging applications. Microsoft and KSAT, which is a ground station network, are partnering on imaging ground stations. On the broadband side, Microsoft and Google are partnering with Starlink to provide connectivity for their data centers. Microsoft also has such partnerships with SES and Viasat. The SES partnership touches both the imaging space and data center connectivity. Another player in the space, Mynaric, which does space laser tech, has a cooperation with a large constellation operator for inter-satellite link connectivity. And these are just the biggest names. These folks, some of them are also presenting at LEOCon, and we are looking forward to great talks from all of them on both sides. Among our attendees alone, however, we can see that there's a huge ecosystem involved. Across the several hundred registered attendees and several people watching on live YouTube streams, we have at least 35 space sector companies, including companies involved in imaging, ground station networks, broadband constellations as well. We also have, apart from these new space players, traditional companies that do networking, like networking vendors providing equipment or software for managing and running networks, cloud companies, telcos, several countries' government agencies, as well as a large number of academics. We have attendees registered from 29 of the top 30 global universities, and 17 of these folks are professors at these universities. Now, keep in mind that this is not 10 attendees from network vendors. This is 10 unique network vendors. Given that there's not that many large network vendors, we have pretty good coverage even in these terrestrial spaces of activity. So there's a lot of interest in this LEO networking space right now. So now let's look at some open challenges and opportunities ahead of us. I'll use this picture as a grounding graphic and refer to research threads of relevance for each of these players, starting with imaging satellites. The challenge here stems from the large data volumes involved, on which I hinted earlier. The satellite to ground station links are extremely limited in bandwidth, and on each pass, a satellite can see a particular ground station for only a few minutes. Further, the uplinks are even more severely constrained. So the path for sending data to a satellite is even more severely constrained, often by as much as 1,000 times. Further, multiple ground stations and satellites create interesting challenges in scheduling. This can be of many flavors. Some of it is well studied in the satellite network systems conferences. However, most of the content there focuses on satellite design or the low-layer hardware design for the wireless channel, not the types of computer systems and computer networking problems that we'll focus on, especially at the higher layers. So there's a lot of opportunity for doing new work here because several of these past methods are no longer keeping up with the scale of these new imaging fleets. Another such research direction that's going to be interesting is potentially applying techniques from video streaming analytics. There's a rich body of work in networking conferences like SIGCOMM and NSDI, with some of this work proposing, for instance, using the receiver side, so in this case, the cloud data center or the ground station, to make decisions on what data to send down selectively from the satellites, right? So adapting these techniques, however, will not be trivial. It will require careful consideration of this type of constraints. Now, you can't tell the satellite from the ground station very frequently what to do because this channel, the uplink, is quite severely constrained. In fact, the constraints are so tight that even TCP acknowledgements are problematic. They can be quite expensive in this context. So this raises another question, which is of how to design efficient, reliable transport protocols. Note that this problem was already known for more than 2 decades. There's even an RFC from several prominent folks in networking about this very issue. However, in the intervening 2 decades, we have learned a lot about transport protocol design. The question that arises is, are any of the new lessons helpful in designing efficient transport protocols for this setting? With that, let's shift to ground station networks. So here again, the demand for ground station capacity is increasing quite rapidly from these growing satellite fleets, but there are a lot of constraints on how we can build and operate ground station networks, where we can place them, for instance. They need, for example, to have large capacity for moving data terrestrially, right, like to data centers. And this capacity is not available everywhere. There's not fiber lines running at every possible location on Earth. So these limitations, again, create several challenges that are worth thinking about. One is, this is the same kind of problem as we already discussed for the satellite side, the challenge of scheduling using the distributed footprint of the ground station network to schedule data downloads effectively. So how do we do that? I think one of the talks, Deepak's talk today, will touch on this problem. How do we resolve the competing customer demands as these ground stations get virtualized, right? So with Azure and AWS both having these ground station as a service offerings, how should they adjudicate between competing customer demands for capacity? Last, how do we design the infrastructure itself? What's the optimal placement of ground stations in a ground station network? There's already a trend towards using data centers, so co-locating ground stations with data centers, but perhaps IXPs, Internet Exchange Points, and cable landing points would also be useful starting points for placing ground stations. So these are all, as far as I understand, open problems for now. Let's go on further to broadband constellations. So here we have thousands of routers zooming about in space at about 27,000 kilometers per hour, making these networks highly dynamic with frequent changes in path structure and the latency of end-to-end paths. This creates several challenges, including across the entire network stack, right? So topology design, routing, congestion control, application performance. I'm being deliberately terse here because the Bopum and Giacomo's talks tomorrow will cover many of these aspects. So I'll focus instead on some challenges that step outside the architecture of the planned LEO constellations. So let's look at the design space using this schematic. So on the x-axis, again, we saw this earlier, is network capacity or market share of some type and latency. So this is just the same schematic we saw a little bit earlier. What I want to add now is another design point in this space where you use multiple types of orbits in the same constellation or same network to provide different types of connectivity. So for instance, you could have a few low Earth orbit satellites, something like on the order of 100 low Earth orbit satellites that meet the needs of latency sensitive traffic. Plus, you can augment these with a few medium Earth orbit satellites, and these serve the goals of throughput from the network. So combining these two, you can build an effective system that might be as good as massive scale in LEO at a fraction of the cost. The only reason this is possible, potentially, is that the vast majority of internet traffic is not latency sensitive in terms of bytes. So most bytes are carried in not latency sensitive traffic, making this kind of strategy potentially workable. So this kind of mixed orbit design is in fact, I think, one of the strategies out there, with the SES being an operator that's exploring this. However, not much is known publicly, and this makes it a nice open direction for research. Another such possibility that uses different types of constellations is to use eccentric orbits for targeted coverage. So eccentric orbits are not circular centered on the Earth's center, but of this type, oblate or elongated. So such orbits, the satellite spends a lot more time over one target geographic area rather than equal time globally. So when the satellite is near Earth, you could potentially use this satellite for low latency traffic. And when it moves farther away, you could use it as a throughput enhancing satellite. And a combination of several such orbits, several such satellites and several such eccentric orbits could provide a good mix of low latency and high throughput satellite connections at all times. So again, this type of mixing could enable systems that are efficient for targeted connectivity in a geographic area rather than global connectivity. I should mention that this type of eccentric orbits were used in military communication systems, but I haven't seen explorations of them at large scale for providing broadband to a target geographic region. With that, let's move out of the new space area and look at more traditional industries and settings. So here again, there are several interesting problems, for example, for network vendors. The ground stations represent a highly unusual operating environment for networking gear, with frequent path structure and latency changes and connectivity changes. And these kinds of connections incur high packet reordering as well as loss as paths change and there are handoffs. Now, this means that there are several opportunities for designing router hardware that operates at these ground stations, and also for control software that controls a distributed network of such routers. One could imagine designing new protocols that maintain connectivity efficiently, taking into account all the routing updates that are happening on the network. One can use the knowledge that's typically not available in networking. In this case, you know quite far in advance what the changes of the network are going to be, except in cases of failure. So the motion-based changes are predictable and known, and those could be used to enhance the efficiency of such protocols. One could also plan traffic engineering, one could plan routes not just spatially, where you think of what traffic to send on which network paths, but also temporally, what traffic to send on which network paths now and into the future. And you could do this to enable smooth traffic changes such that there are not sudden congestion points from satellite movement causing path structure changes. With that, let's shift to the next industry segment here, cloud or content companies. So here again, the sophisticated operators like Google, Microsoft, and others build custom sophisticated software-defined WAN wide area networking solutions. However, the LEO links that we are talking about are very different from today's WAN fiber links for the same reasons I mentioned earlier with latency changes, packet reordering, high bit error rates, random loss, etc. So are the software-defined WAN networking solutions deployed out there mature enough to handle these dynamics from these LEO links? Is that the case, or do we need more new work here? I'm leaning towards the latter. That's why this question is posed here. Further, even though you have these, let's say, routing mechanisms and software-defined network mechanisms to enable such multimodal connectivity, how do you best use it effectively for enhancing application performance? How do you select what traffic goes where at any time? This again is non-trivial. Last, there's a potential for value in the cloud operator or content network operator getting a raw, no FEC, no forward error correction link from the satellite network operator and using its own software techniques to do that, depending on different applications' needs for correctness. So some applications might be okay with a few bit errors, and others will absolutely not tolerate them. And taking this control away from the satellite network and doing this in-house with knowledge of the application needs might be another direction to explore. I'll skip over the last one here in the interest of time. So next, let's look at the ISP and telco industry. Here again, there are several new market-based challenges. Two, for example, are that not everyone will want to spend a 500 franc fee on a user terminal for these broadband constellations. Even enterprise customers might not want to send all their traffic to the satellite network because this kind of connectivity will probably be more expensive than fiber. So this raises a couple of questions. One being, could the ISPs and telcos create managed services for enterprise customers such that low latency traffic is selectively transmitted on the satellite network for long distance communication, of course? So these links, as I mentioned, over long distances can be faster than fiber in terms of latency. And there's potential for ISPs to create managed services that integrate them with high throughput fiber links such that applications can benefit from the best of both worlds. Google, Microsoft, etc. can do this for themselves. Most enterprises will neither want to nor will have the capabilities to do this. The other aspect is to try to resell this expensive satellite broadband connectivity to consumers using cheaper last mile technology. So what are the various methods in which this might be accomplished? That might be another potential direction to explore. Next up, government agencies. These LEO broadband constellations provide a new type of broadband offering. There's several characteristics that make it easy to use for providing broadband to a lot of people, but there are also these expense-related factors that we just talked about in the ISP industry as well. However, they do show that the barrier to broadband via space is much lower than one would have expected perhaps 10 years ago. So again, how should governments adjust their policy making, for example, for goals like broadband for all? So how should these new broadband offerings factor into that decision making? Second, is it worth building country-targeted constellations? Is this something that governments should consider to serve their own populations? Lastly, for my own people, academics, all of the above, these are great spaces to do research in. It's all fertile ground. I'll touch on one additional specific actionable item. I've been planning for a while a platform, a testbed for experimentation on satellite networks, SatNet Lab. The name's inspired by the Planet Lab testbed, not to be confused with Planet Space Labs, from whom we'll have another talk later today. The idea here is to start with university sites with equipment, user terminals from networks like Starlink, and use these for experiments, for measurements, to test congestion control, to test application layer performance, and produce methods that improve this performance. While initially I had come up with this idea of the platform for broadband constellations, I think there's actually room for doing this for imaging applications as well. For instance, collaboratively launching nanosatellites for research. So if you're interested in more, please check out this editorial I wrote for SIGCOMM CCR to learn more and get in touch if it interests you. So now let me briefly summarize the agenda for LeoCon. We have 10 exciting talks, 5 on each day. We'll have plenty of time for questions and breaks. We have budgeted 15 minutes after every talk, except this one, in which we'll keep 10 minutes for questions and 5 strictly break time. We'll also have an industry panel at the end of the day, which I hope will be very exciting and let us engage with our panelists, our speakers from the industry, to learn more insights. I want to close by thanking my co-organizer, Debopam Bhattacharjee, who did a lot of the heavy lifting in making this event hopefully a success. We'll find out by the end. And Ilham Isani, who's helping us with moderation and management behind the scenes. Thank you both. You're welcome to connect with all of us via email and LinkedIn as you may wish.